Hello. It's been a while, and I've got something a bit different today. It's not a game, although I did work on a game for a bit, but then gave up. But whatever. So in programming class, which I have in college, we started talking about data structures, and we talked about arrays and what are they called? Uh, Linked lists, And I was like, hey, what about a tree? That would be fun to make. So I did. It took me a while. So how it works is when you create. Sorry for the flashbang here. When you create the tree, you you must uh, add the common ancestor, because how my tree works is that each node can have multiple children, as many as they want, but a child can only have one parent. Therefore, uh, the whole tree has a common ancestor. So what I did is that when you create the tree, you add automatically the common ancestor. And so if you look at the constructor, if I can find it somewhere, uh, where's my constructor? Oh, here. Not sure why it's here. See, you must specify an ancestor. If you don't know what this notation here means, is that basically you can make a tree of any type. You can make a tree of ints, a tree of booleans, a tree of floats, a tree of whatever class you may have created. Um, and yeah, so let's go into more details. So as I said, the trees is made of nodes. And if you look here, I have a class that's embedded inside of my class, which is the class node. And basically, the node has has three parameters. It has the value of the node, but it also has a reference to its father node. So if we're talking about this node here, its father node would be this one. And oops, I didn't want to open this. Um, and it also has a reference to a list of all of its children nodes. So if we go back to this guy, it would have a list with two elements, being this one and this one. This just makes it easier to navigate. Also, I must mention that this type of data structure works well in small quantities, but at large scale it is extremely slow, because the only way to loop through all of the elements of the tree is with a recursive function. So this here is my function find. Because the class node, the main program will never access that. The main program only knows about the value inside. So yeah, this is a recursive function. How do I explain this? Well, let's go through the process of adding a new node, okay? This is going to make it sound more reasonable. So let's say you want to add a new node as a children of another node. So let's say you have this node and you want to add a children to it, which would be this one. Well, so you say, okay, I want to add the children under this one. Well, my tree is made of nodes, it's not made of values. So I must find the node. I must find the node. Yes, this just makes sure that you haven't already added a node with that value, because I added, for some reason, I decided that inside of my tree you couldn't have two identical nodes, but it doesn't matter. So this basically just says if it's already in the node, crash. So here I must find the father's node. So to find the father's node, this calls this function here, which in turn calls this function. So it says, where is it? Yeah, it says, yeah, find the node with the value starting by the ancestor node, which is the common ancestor. So it goes through here, and it's like, okay, am I the correct node? No. Let's look at my first child. Is this the correct node? No. Let's look at my first child. Is this the correct node? No. I don't have a child. Let's go back. Is this the correct node? No. I don't have a child. Let's go back. And it does that until it's found the correct node. So you see how slow it is. It calls itself within itself within itself until it finds the right node. And it's slow, but there's no other way to do it because it's a tree. You have to make a recursive function. So if you look inside of the function find, you call the function find for each children of the node. And it does that until it's found the right node. And if the node is not inside a function, it returns null. And as I said, if the value you're trying to find is not null, that means that it's already in the tree, so it calls this exception. And if the father is the node, so if there is no father, well, it calls the inexistent exception. I hope this makes sense. I'm having a difficulty explaining it, but it works. So yeah, I have this function add. I also have the function get father. I have the function get children. So basically, you're like, hey, please return me the value of the father I'm giving you. Please return me the value of the father of the value I'm giving you. Please return me its children. Here is where it gets interesting. Let's say you have okay, I'm gonna just redraw the tree because this is getting out of hand. Oh, yeah, okay, whatever. So let's redraw the tree. This is a bit big. All right, so all right. So let's say you have this node right here, and you're like, all right, I want to remove everything under it. Well, you can call the... Oh, this should probably be renamed by remove branch. Yeah, because it doesn't remove their descendants. It also removes itself. So, this function right here, it says node.father.children.remove node. So what does this do? Well, it says this is the node and this is the father. Remove me from my father's children list. So basically we're breaking this link right here. So since we're breaking this link, everything under it doesn't exist anymore because the main tree doesn't reference it anymore. And then also we're saying node.father equals null. This is not necessary, but we're breaking the link in both ways, not only this relation, but also this relation. So that's the remove branch. There's also the add branch. So let's say we have... No, stop opening Google. I'm watching a Minecraft video if you're interested, by the way, but so let's say we have a second tree right here. And we're like, hey, what if we took this tree and linked it right here? Well, that's basically what this function does. First, it checks if it can be merged, because if you remember, I put the restriction that there cannot be twice the same value in a tree. So basically it checks for each element of this tree, is there an element in that tree that's the same? This is a really slow process because we're basically making a recursive function for this one that calls a recursive function for this one. So yeah, it's really slow, but it works, and I don't care. This is basically counting all of the descendants. So I'm saying, hey, if I start with this node right here, how many descendants do I have? And it counts all of them. This move branch, this one's interesting. All right, we're gonna start over again because, yeah, it's a mess. So, what? Oh, I didn't know I could do that. I broke my. Okay, there you go. Okay, there you go. So, the move branch function is like, hey, let's take this node and everything under it and move it right over here. And that's basically what it does. It's a super easy process. It basically just breaks this link right here and recreates the link right here. It's a really fast and easy process. Because in C Sharp, objects are not really objects. They're basically just references. So you just say, hey, stop pointing this way and point that way. It's a super easy process. This one, I don't know why I included this one. It's not really a useful function, but I was like, hey, that's fun. So, uh, let's remake the tree. All right. So let's say you take two nodes. So let's take this one and this one. And you choose one as the base. I'm going to choose this one as the base. And you're like, all right, so how many generations away are their common ancestor taking this one as the base? So you count. This one takes 1, 2, 3, 4, 5. This one takes 2. Since we took this one as the base, 5 is the answer. But the common ancestor of the whole tree will not always be like the common ancestor of these two nodes, but in this case it is. So how it works is it counts how many turns it takes to the common ancestor of the whole tree. So in this case that would be 1, 2, 3, 4, 5, 6. It puts all of them in a list, and then it counts from this one up until it finds something within the list. So 1, 2, and it takes the index of the list. This index would be 0, 1, 2, 3, 4, 5, and it returns that number. So 5. That's how this function works. Is brother, that's really easy. It checks if both of their father are the same guy. Let's take another go. So if their father to both of them is the same guy, then yes, it's a brother. Cousin is the same thing. If their grandfather is the same guy, then yes, they're cousins. So those are the two final functions. So yeah, that's what I did today. Why? I don't know. I did this during English class, which is a bit weird, but you know, whatever. It was really fun. I'm not sure if it's ever gonna be useful to me, but yeah. Uh, what can I do now? I guess we can test it, right? So let's create a tree of integers for now because wait, why is it not working? Oh, I got it using structures. No, structure. Is that the name of my structure? Struct. Yeah, there you go. So let's make a tree of integers. Let's call it t equals new. As I said, I made it so that you need a default value for the common ancestor. Let's just make it 0. Let's now make an int called one. That's 1. Make an int that's 2. So now we can do t dot add the value I to the ancestor 0. And now we can do t dot add the value j to the, let's say, ancestor I. Oh, I forgot an equal sign here. And then just for fun, we can do t dot add, let's say, 91 to the common ancestor 0. So basically what I just did here is I made a tree, and here is 0. I made a child, here is 1, which has a child, which is 2. Is that it? Yeah. And then I also added another child to 0, which is 91. This is the tree I just created. We can... Yeah, you just saw my background here. These are the games I play, whatever. I'm probably gonna blur it out. So we can verify this if I do console.writeLine, let's say t dot father get father of let's get father of 2. So if in the tree the father of 2 is 1, so if I run this, it's going to say 1 right here. So yeah, that's how it works. Thanks for watching. I'm gonna have to do a little bit of editing so you don't see my desktop, which I have accidentally exposed. Okay, bye-bye.